Hello, my name is Scott Grizzard from the University of South Florida. This is Discrete Math on the 27th of October, fall 2020. And today we are going to be continuing our discussion on induction and recursion. This will be part 3. Hopefully next, this will be the last one that's just on induction and recursion. And then we'll get, we're doing applications already because that's kind of our examples. But then we'll get into some of the other number theory stuff that we need for RSA. Let's go ahead and talk about the quiz. I know that many of you haven't turned it in, so you're getting to see the quiz review before the quiz. Okay. I'll just do it anyway. Okay, so I've fielded a couple of questions about this. So if P is a prime number, which of the following must be true? And then people have said, well, what if P is 2 or P is 3? And this notation is confusing, okay? So there's just kind of this convention that I need to say. So there's a convention. The set 2, 3, ... P minus 1 is the notation for all positive integers between 2 and P minus 1. Okay. Now, this notation is actually confusing because 2 and 3 are both primes and so is P. So why isn't this all prime numbers with, 2, 3, blah, 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 blah? And that's a good question too. Or why isn't it, what if P equals 2? Right? So now I've got this set like 2, 3, ... 1, and that's nonsense. Right? If P equals 2, then 2, 3, ... P minus 1 equals the empty set. 2, 3, if P equals 2, if P equals 3, then 2, 3, ... P minus 1 equals 2. All right, and if P equals 4, which it can't be because I said P was prime, but you get the idea, then this set 2, 3, ... P minus 1 would equal 2, 3. Okay? How do we feel about that 1 to 5? That's a convention. And people were asking questions about it, so apparently I didn't give you a thorough heads up about that. But that's just the convention. It's kind of like any language. Math has a few irregular verbs and irregular nouns, and this is kind of one of them, right? The worst one, by the way, total aside, in calculus, why is it that sine squared of x equals sine of x times sine of x, but sine negative 1 of x does not equal 1 over sine of x, right? Why is that true? Why is sine negative 1 of x equal to arc sine of x? And it's just because math is in one sense a language, and it's the oldest things, by the way, that are the worst. In any language, right? In any language you study, you can bet that the verb to be is irregular. It just is, right? That's, whatever you're studying, the verb to be is probably irregular. And that's because these are the oldest part of the language that stick. Okay? They're kind of the things that get used often. So they've got their own kind of unique thing. And this is like that. And this is like that. They're just conventions and they're irregular verbs. Especially that sine stuff, right? If you look at the verbs for like the common thing, if you look at the things that you say all the time, they're probably the things that are irregular. English is a little bit better. English, French, the big languages are usually better at this because they've been slimmed down a little bit. But you know, in I mean, even in, you know, in most languages, the things you say all the time are the things that are irregular, especially things like to be. And it's the same thing here. This is used all the time, therefore it's kind of got an irregular convention meaning. Okay, so let's get back to the quiz. So for all k, all integers in 2, 3, so for anything between 2 and p minus 1, p mod k does not equal 0. Right? That's true. Right? That's the definition of what it means to be prime. For all k here, k to the p minus 1 mod p equals 1. And that is true. And it's also true if we include 1. This is a version of Fermat's little theorem. Note, it works for k equals 1 also. Okay. P is a zero divisor. That is not true. Nope. P divides every positive integer. Well, P does not divide 1. I don't care what prime you're using. Nope. And for all a and zp minus 0, you know, so this is the set minus thing, remember? This is zp except for the set, except for 0. Whenever a exists, this is true. Okay. So 1 to 5, how do we feel about this problem? Okay. Right, this is just like variations on the definition. This should be zoomed in more. Right, this could have been 1 through p minus 1. I just left it as 2. But it's still true, right? If it holds for 2, 3, blah, 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 p minus 1, it also holds for 1, 2, 3, blah, 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 p minus 1. I mean, I'm sorry. If it holds for 1, 2, 3, blah, 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 p minus 1, it also holds for 2, 3, blah, 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 p minus 1, right? It also holds for 1, but it, you know, I could say it without including the 1. This one I can't, because p mod 1 does equal 0. Okay. Are there any questions about that? I got questions going in 2 places. There's questions on Twitch and there's questions in Discord. And I checked this time. You can type. Apparently, at one point, I messed that up. Okay. All right, let's look at this one. So my idea here was that you know, grab it and play with it and see what happens. So what I'm saying here is that, okay, I've got lines 1 through 12 where 12 is blank. If I put a line recursion 1, 10, how many times would the program output UGA? Okay, so let's see. N starts at 10 and is not 0, so I'm going to go 2 down. N is now 8. So I've got a UGA for 10. I've got a UGA for 8. I've got an UGA for 6. I've got an UGA. Go back one more. I go 4. I got an UGA. I did a 2. And then I get to 2 minus. I go from here. This is a 0. When I go in, I get a chaka. So it's UGA, 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 chaka. Okay. Yeah. Okay. I love how you guys call it the Guardians of the Galaxy song. I mean, when I was growing up, it was the Ally McBeal Dancing Baby song. So, you know, it's been a while to while. And it was around before that. So the answer there is 5. Now, if I put in 11, I'm going to get the following. Ooga, 11, Ooga, 9, Ooga, 8, Ooga, I'm sorry, that should be a 7. 5, Ooga, 3, Ooga, 1, Ooga, -1, Ooga, -3, D. Okay. So this is going to go on forever. This is infinity. All right. It's like a while loop without a break. How do we feel about this little chunk of code, 1 to 5? I don't have as much elbow room as I used to in the thing, right? I had the cat, not my cat, the other cat, the outdoor cat, was in kitty jail because he got attacked by another cat and needed antibiotics, and he peed on my green screen. So when I had to wash my green screen and then redo it, and when I did it, I kind of cut in so I could get to more of the books on the bookshelf, and we could get behind it and stuff. So, you know, there's less space behind me on the green screen. I could probably get an even smaller one if I wanted to, and have it do stuff. Okay. Yes, my poor little cat. It's not my cat. So it's my mother's cat. When coronavirus came, you know, I'm hunkered down with my mom because she's single and I'm single. And so we were like, oh, let's just pool expenses, and, you know, so I'm living at my mother's house. You can say that my math professor lives with his mother. Yes, I do. You know. But one of my mother's cats, because it's the outdoor cat. No, there's no problem set due this Sunday. So if we put 4 to because 4 is not prime. Oh, wait, no. If you do 4 to the 2 minus 1 mod 2, because 4 equals 0. So there's a question, if this is right, so here's the question. Why is 4 to the 2 minus 1 mod 2 equal to 0? And the answer is because 4 equals 0. Right, so this right here is 0. Mod 2. That's why. Right, so if I look at my statement was that, my statement here was basically that P had to be, the base had to be less than, right here, the base had to be less than P. Does that answer your question? Okay. All right, so let's go on over here to, the day stuff. But K is 4, P is 2. Yes, but look at the statement, unless I messed up the statement, which is entirely possible. Yeah, so for all K, but notice that K has to be less than P. Right? K is in this set 2, 3, right? So 1 works for 2, right? So if I should have put 1 here because it's true also for 1, but 2 doesn't work because 2 is P. Okay? So the base has to be less than P. It has to be P minus 1 for this. The other version says that the other version would be NZP. So let's look at the other version. Okay, so let's look at Fermat's... So let's restate this. So if P equals... Okay, so if P is prime... then for all base B in ZP, ZP minus 0, B to the P equals P minus 1 equals 1. Okay, and why should that be so? And you had P equals 2 and B equals 4. But B here, but B equals 4, which equals 2, which equals 0 in ZP. Right, because you have Z2. Does that make sense? How do you feel about that 1 to 5? It's a good question. It's an easy thing to confuse, but I was restricting in the thing. Well, yeah. So the number here in this K is the base, right? K to the P minus 1. So this K, if P is prime, then this K was, and again, 1 would work here. 1, 2, 3, P minus 1, blah, blah, blah equals 1. So if P is 2, my only choice would be 1. And there would be no choice in that version. Where I said it before. Right, because this base equals 4 equals 2 equals 0. So you determine this mod. So either the question tells you what it is, or the mod tells you what it is. So here the mod was P, and here the mod was K. Okay? So you determine it based on what this says. Right? So because I'm dealing with mod P, I'm actually in ZP. Okay. And that's sort of the point. When I deal with integers modulo something, I'm actually dealing with this group here and not with ring. And I'm not really dealing with the whole integers and then modding. What I'm really doing is just playing around with these remainders, with these things, with these little rings. Okay. So today what we want to do is we want to play around a little with, really Binomial Theorem should go up top because I guess we can do that first. So we've already proven the Binomial Theorem. And our proof is this kind of nice little combinatorial proof that we had so far. Oops. I'll stick you right here. Okay, so the proof we had so far, let's just state it. Come on, zoom in. Okay, so the proof we had so far for the binomial theorem was this nice little trick. Okay, so we had this, so let's just state it first. So stop that. It doesn't know the difference between me hitting it to make it shrink and me hitting it to type something. That annoys me. Okay, so let's just state the theorem. Stop that. So the theorem said the following. A plus B to the n equals into 0 a to the 0 b to the n. I may have done it the other way. Which way did I do it? Did I do it a to the n, b to the 0? I think so. Plus n, choose the exact same statement. To the n minus 1, b to the 1, plus dot, 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 plus a to the a to the, oops, I need the n choose n. N choose n, a to the 0, b to the n. Okay? So I have this theorem, and our proof right now, the proof we did at the beginning of class, involved this kind of card trick thing. Okay? And it's a nice proof. It's a beautiful proof. It's one of my favorite proofs in all of math. And there are a lot of really pretty proofs in math. This is one of my favorites. But it's a hard proof. You have to sit there and play with it before you can convince yourself. And there's another proof based on induction that I want to do for you today that demonstrates this idea again between a hard proof that's hard. It's a combinatorially hard proof in which the hardness is sort of one-off versus recursive proof where the hard part is just the recursion itself. So once you understand recursion, the proof is actually convincing very quickly. You don't have to sit there and think about the proof for an hour and a half after you get the recursive trick. Let's look at this proof again. Using recursion. And I'm going to need some pieces that we've talked about before. So I'm going to throw Pascal's. Normally I would call this a lemma, but I'm just going to throw Pascal's identity up there. So I talked about this before. This is also known as the proof that you either sit on the committee or you don't type thing. And we're not going to prove this. There are several proofs of this. I did one where I made an argument based on cards or committees. You can do if you feel like it, you can do a formula proof on this one. I'm not a fan of formula proofs, but if you want a formula proof for this, so formula proof for Pascal. I'm not a fan of formula proofs, but this is n false k over k factorial. And what I'm saying is that equals n false k minus 1. So here's what I'm saying. So I've got this right-hand side, RHS equals n false k minus 1 over k minus 1 factorial plus n minus 1 false k minus 1 over k minus 1 factorial, which is nice because it's a common denominator. Let's do this. Right, now I've got a common denominator of k minus 1 factorial. And then I've got an n times n minus 1 times n minus 2 times dot 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 times n minus... Now this one's tricky because normally it would be n minus k minus 1, but since I'm only going k minus 1, it's n minus k. I'm sorry, k. It would normally be k plus 1, but now it's k plus 2 because I'm only going k minus 1 of these. Plus, and then I've got an n minus 1, and then I've got that same dot 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 again, but this time I've got an n minus k plus 1 plus 2. And then I've also got the n minus k. Do I have a k minus 1? Oh, yes, because I'm starting at n minus 1. So that's a little tricky on that formula proof. You have to be careful on that formula proof if you want to do it. It's not to say that you shouldn't. I mean, I dislike it strongly, but that's okay. So all of this right here, these two terms here, this term right here, and this term right here is in common. So I wind up with an n plus n minus 1. I'm sorry, n minus k plus 1 times all this stuff. This is n minus 1 falls, I'm sorry, this is n minus 1 falls k minus 1. And I've still got a k minus 1 factorial down here. So if I multiply the top and the bottom by k, I wind up with a k factorial on the bottom, and I like that. And those are nice. So I've got, and then notice I've got here, I've got a 2n, and then I've got this negative k plus 1. That's going to be unpleasant. Let's just hold on for that. All right. Now what I'm going to do is I'm going to hit these things up. Okay? So what am I missing from the top? I'm missing an n, so what's missing? I'm missing an n. What else am I missing? I need an n here because what I want is n false k. And I need a k minus 1. I need an n minus k plus 1. Well, here I've got an n minus k plus 1. I've got a k. And I've got a 1 here. How can I fit all that together? I'm going to make sure I got my other steps right before I just keep going. All right, so this was here. I stopped k minus 1. So that last one would be k plus 2. That's correct. This one would be n minus k minus 1 because I started at n minus 1. Right? And then I have this term and this term all together. So I stick all of that together. And now what I'm missing is an n on both. Right? I've got one n. I need another one here. What can I do? Okay. I'm going to do something I don't do often. I'm going to say you figure it out. It's on Wikipedia. Now, And make sure I didn't make a mistake up here because I am missing a term somewhere. Anyway, I can do this with a nice little number proof. I just have to sit there and look it up. I think this is the way you start it. That is. Ah, crap. Now it's going to bug me, isn't it? Anyone want to chime in? Where am I missing it? What am I missing? The N, that's right. The K is right. So this becomes an NK plus NK minus K squared plus, this becomes a 2NK. K there, I have a K there. How do I get a K minus 1 out of this? All right, because if I come up here and I put a K here, and I put a K here, what am I looking for? Am I looking for a K plus 1? This is the numeric proof for this, for Pascal's identity. And this is the oh, what the heck, I'll look it up. So I did that right. It's that one. It's that one. Something's wrong here. Oh! This is wrong. Duh. Sorry. Nope, that's my major mistake. Sorry. I would have caught it when I did the proof for the other thing. That should be n minus k. Duh. It's n minus 1 choose k. There we go. That's better. That's where the other k comes from. So this one is actually a k here. Duh. There's a k here as well. So this one's k factorial on this side. There it goes. So now, when I take a common denominator, that's where the other k comes from. Okay. So this should be all over k factorial because I took a common denominator. So I multiply both sides by k and I get a common denominator. That's beautiful. Now, when I take this out, I get the k is no longer common. So this becomes a beautiful, beautiful. So what comes out here? The n minus 1 times, so this k is gone, this is gone, this still factors, and there's a kn there, so this becomes kn This is right, that's right now, this is k, so this is a, when I factor this out, this is a kn times an n minus k plus 1. That also comes out. That's it. That's now right. Oh, it's one of those days this morning. All right, so this now, I've got a k in here plus an n. So this right here becomes a k plus 1. Times n minus k plus 1. What am I supposed to take out? What am I missing? I'm missing the n minus k plus 1. So something has to divide out. I'm missing an n. Why is that plus 1 there? Right. The plus 1 has to come out of here somewhere. Where is it? So this becomes n plus n. No, this is not. That's separate. This becomes n minus k. So this becomes n minus 1 times k. There's the n minus 1. And there's a plus 1 here that I don't remember how to deal with. Anybody got an idea? Right, because the k factor's off. That's where the k come from. I don't remember. There's another thing I'm not factoring off, right? Because one of these is n minus 1. That's that. Right, that goes in there. Somehow I need an n on both sides. I don't remember. There's something in here. I got part of it. I don't remember the rest of it. It's on Wikipedia. I'll find it later. But there is a numeric proof for it, and I hate the numeric proof of it. There is one. I will fix it later. Let's move on with life. Let's see. So I've got the statement right, though, right? I've got... No, I don't. That's where the other one is. It's right there. I flipped it. Come here. That's where the other mistake is, right there. I got the thing wrong. I put the k minus 1 here, and this was supposed to be an n minus 1, not a k. Whew. That's where I messed it up. Okay. And I'll fix the rest of it later. That's what it's supposed to stay. That's what I get for trying to do them from memory without looking it up. Yeah, so I'll have to fix this later because I messed up the top part. The top parts were supposed to be matching, not the bottom part. Anyway, now that you have no faith in the idea that I know how to do math, and you are totally convinced that I seriously don't need to know what I'm going on. Yeah, that's what I changed. So someone in Twitch chat pointed out my mistake, which was the same. So now that you have no faith that I know how to do math, let's do this one. So we had this kind of combinatorial proof. Let's look at it again using recursion, and I am going to do this. So if n equals 1, this is true. So my base case is going to be n equals 1. All right, so let's let n equal 1. Then a plus b to the 1 equals a plus b, which equals, okay, well, 1, 1 to 0, a to the first, b to the 0, plus 1 choose 1, a to the 0, b to the first, since 1 choose 0, b to the 0, 1 choose 1, and a to the 0 all equal 1, and I can always multiply by 1. So 1 to 5, how do we feel about the base case? Okay. The idea is that a plus b to the 1 equals, well, just a plus b, right? Because it's 1 multiplier, I mean, to the 1, it's itself. And then 1 choose 0 is 1. 1 choose 1 is 1. B to the 0 is 1. And a to the 0 is also 1. So I just multiply a bunch of 1s in. I can always do that. That's the idea. All right, so let's let in arbitrary and assume that for all m less than n, a plus b to the m equals m choose 0, a to the m, b to the 0, plus dot 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 plus m choose m, a to the 0, b to the m. All right, so that's kind of my induction assumption. Okay. Okay. Someone's asking for code for, I think, this. I haven't written code for this. I've written code for the others. I think I posted all the others online, but if I'm missing one, tell me. All right. So now what I'm going to do is I have this true for there. So now let's look at it. A plus b to the n equals a plus b to the n minus 1 times a plus b. How do we feel about that, 1 to 5? Right, this is the induction hypothesis. Okay, and then here I've got n, and I'm just going to have, I have n minus 1 here, right? So like I'm taking a plus b to the 4th. Well, that's a plus b cubed times a plus b. And I'm not using contradiction to prove this. I'm using induction. Okay. So I'm going to show, so I want to show if it holds for all m. So I want to show if it holds for all the rungs under me, then it holds for the current rung. Okay. And people are saying they don't understand how induction works and recursion. That's why I've spent 3 days doing examples of it. Okay? And if the time limit looks like it's going to be what it is, it may be 4. Okay? So if it holds for all m less than n, then it holds for n. This is what I want to show. Okay? So now what I've done is I've got a plus b to the n, and that equals a plus b to the n minus 1 times a plus b. So now I've got something on the induction hypothesis. Now, what I'm going to do is I'm going to multiply these two out, but this one I'm going to use my induction hypothesis. So this is going to equal m choose 0, a to the m, b to the 0, plus dot, 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 plus m choose m, a to the 0, b to the m, times a plus b. Now, I'm about to multiply this very, very carefully. Okay? What I'm going to do is I'm going to multiply this out like I was foiling it, but writ large, right? There are m terms in here. Actually, there are m plus 1 because I start at 0. Okay, and now what I'm going to do is multiply it out. So I can think of this as what's going on here is I've got 3 to the 3a cubed plus, this should be a cubed alone, a cubed plus 3a squared b plus 3ab squared plus b cubed. And now I'm multiplying this by a plus b. This is what I've said, right? This right here is by the binomial theorem, and now I've got another a plus b. If that helps you do a little bit more concrete. All right. So how do we feel about this little step, 1 to 5? Okay. So what I've done is I've applied What I've done here is I've applied the binomial theorem to this. Right? That is what came before. In the same way, if I knew the binomial theorem worked for, here's the example, right? If I knew that this worked, right? So a plus b to the 4th equals a plus b cubed times a plus b. And I said it worked for 3. All right, so if it worked for 3, what I'm going to do is apply it for 3. Okay, to the kth case. Should be m equals 3 case. And now what I have is this thing just hanging out. Okay. So 1 to 5, how do we feel about that? Okay. I'm trying to show this step using an m of 3. The whole thing is an n of 4. Right? So I'm just kind of demonstrate this step in a little bit more abstract, at a slightly more concrete manner. Now what I'm going to do is I'm going to multiply this term by a plus b, and I'm going to be very careful on how I do it. So this is how I'm going to do it. This whole thing equals, now, I'm going to have some extra spaces, and I'll show you why here. I'm going to multiply a by all of this. And then I'm going to multiply b by all of this and sum them all together. Yes, that's the thing I'm doing. So now what I'm going to have is when I do this, I'm going to have m choose 0, a to the m, b to the 0, plus m choose 1, a to the m minus 1, b to the 1, plus dot, 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 plus m choose m minus 1, a to the 1, b to the m minus 1, times m choose m, a to the 0, b to the m, times a, plus, and then I'm going to do the whole thing again, and then times b. That should be a plus, not a times. Okay? That is the exact same thing. What I just did was I said this. And the more concrete example, what I said was that this equals a cubed plus 3a squared b plus 3ab squared plus b cubed times a plus a cubed plus 3a squared b plus 3ab squared plus b times b. Okay? And these are all being added together. 1 to 5, how do we feel about that? All I did was distribute this plus. I took this whole block, multiplied it by A, and then I took this whole block and multiplied it by B. Okay? Just like we did it in 9th grade. Or 8th grade, or what grade was that? Was that 7th grade? Algebra 1. What is that? 7th, 8th, or 9th grade? Okay. So now what we're going to do is now I'm going to multiply in the A. Okay. Moreover, the other thing I'm going to do is I'm going to set this up very, very carefully. I'm going to evaluate m choose 0 and m choose m here, okay? So what I'm going to do is I'm going to set this up very, very carefully. I'm going to have, I'm just going to leave this as a 1. I'm going to have a to the m plus 1, b to the 0, plus m choose 1, a to the m, this would be a to the m, b to the 1, plus m choose 2, a to the m minus 1, b to the 1, plus dot, 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 plus m choose m minus 1, a squared, b to the m minus 1, plus, and then I've got this kind of 1 here, m choose m, a to the first, b to the m. Plus, now, I'm going to leave a space. Okay? And then I'm going to have another one at this end. And these are special. This one's going to be m choose 0, a to the m, b to the 1, plus m choose 1, a to the m minus 1, b, let's see, this was b to the 0 here. So this one was b squared. I screwed this. Oh, I did screw this one up. This should be a b squared. Sorry. That's right. Plus, dot, 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 plus. So this b squared term came from that middle there. This term here is going to be from the middle here. So this is m choose m minus 2. A to the squared, because I've got a 2 there, b to the m minus 1 plus, then I'm going to be multiplied by that term, m choose m minus 1, a to the first, b to the m, and then I've got this last term, and I'm going to evaluate this last m choose m, and I know I'm running out of space here. Ooh, what are the nice things about the computer as opposed to the board? Excuse me. I could put more board space right in the middle. Plus, and now I'm going to evaluate this m choose m. A to the 0, b to the m plus 1. Okay, so the tricky terms are the fact that this term here became that term there, and that term there became that term there. Now, I pulled some of these out of the middle here, right? So this m choose 2 came from right here. So this m choose 2 came from the dot, dot, dot. That term came from the dot, dot, dot. And that term came from the dot, dot, dot. Okay. All right, let's look at my little example here that was going on. I know that is confusing because there's a lot of things to keep track of, and that's kind of typical of these proofs. You kind of, they're exercises in bookkeeping. Okay? But, again, the hard part, once you understand induction, the hard part is recyclable. This should be a b cubed. I don't know what happened to the cube there. Now, to look at what happens here, I'm going to take this a cubed and make it an a to the 4th. All right, because I'm multiplying it by an a. Here, I'm going to have a plus 3a cubed b plus 3a squared b squared plus b cubed a. That's the top line. And then the bottom line, I'm going to leave this space blank, right? This is blank and this is blank. And now I'm going to do the bottom here. So I'm going to have a cubed b plus 3a squared b squared plus 3ab cubed plus b to the 4th. So how do we feel about that, 1 to 5? What I just did, I took these two things and I made a little bit of space. Okay? So I can think of this as kind of like the same thing I do when I'm adding like 10 and 5, right? I add the ones column down and then I add, well, I mean, you add from right to left when you're doing it, when you're not doing it in your head. So on paper, I would add the, if I was doing this, if I was doing 105 plus 10.3, right? What would I do? I'd line them up like this, and I'd add them down. And that's kind of what I'm doing here. Okay? I'm kind of adding down columns. Okay? So all I did was I took these two expansions and I just multiplied it out. Now, let's look at what happens over here. When I do this, I'm just going to add down a to the 4th plus, this is a cubed b, this is a cubed b, so I'm going to get 4a cubed b plus, and then I'm going to add down here, I'm going to wind up with 6a squared b squared plus 4 this, I don't know why that's a b cubed. Oh, because it was out, right? B cubed a is the same thing as ab cubed, right? So this is going to become ab cubed plus b to the 4th. right? I just added down the coefficients. Just like I was doing if I was adding numbers. And this right here is equal to a to the fourth. These are the binomial expansions, right? This right here equals, what is this? This is 4, choose 1, a cubed, b. This is 4, choose 2. 6 is 4, choose 2, a squared, b squared, plus 4, choose 1, a, b cubed, plus, and then, of course, the two zero terms. 4, choose 0, a to the fourth, and this is 4, choose 4, b to the fourth. I could put b to the 0 there, but you get the idea. Okay? Okay. So now I've got this. Now I'm going to apply Pascal's identity. So now I've got this term over on its lonesome. Now, m choose 1 plus m choose 0 is n minus 1, right? M choose 1 plus m choose 0 is m plus 1 choose k. Now, m choose 2 and m choose 1, that is the same as m plus 1, not k. I'm sorry, that should not be k. This is m plus 1, choose 1. This right here is m plus 1, choose 2. This right here is m plus 1, choose m minus 1. This right here, a squared, b, m minus 1. This right here, m choose m plus m choose 2. This is m plus 1, choose m. And then I've got this kind of a to the 0, b to the m plus 1 hanging out. And then recall m equals n minus 1, so m plus 1 equals n. So I've got a to the n, b to the 0, plus m plus 1, that's n choose 1, a to the n minus 1, b to the first, plus n n choose 2, a to the n, b to the 2, plus dot, 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 plus, this should be a to the n minus 2, b to the 2, plus, dot, 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 this is n choose m minus 2, a to the 2, b to the n minus 2, plus n choose n minus, this should be an n, not an m, n minus 1, a to the 1, b to the n minus 1, plus a to the 0, b to the m plus 1, which is a to the b to the n. What sign did I lose here? I lost an equal sign. Okay. And then what I'm going to do is I'm just going to, now all I need is these little things. Well, these are both 1s. So I'll just okay, well, this 1 equals, I just fill in the ends. A to the n, b 0, plus dot, dot, dot. I'm not going to write all that stuff again. And this 1 at the end is n choose n, right? Because it's a 1. 1 is n choose n. A to the 0, b to the n. And that's the proof, right? I scoop down, I grab something I could use, and then I induct. 1 to 5, how do we feel about that? What we were looking for was the fact that n, we wanted to show that if it held for m, then it held for n. Okay, so just like here, if I have it for 3, I get it for 4. I understand you feel lost, but you know, this is, you know, it is what it is. It is a proof. It's got a ton of algebra in it, and it's difficult. And this is not the pretty proof, right? I mean, I did the pretty proof. The pretty proof is the one with, you go, okay, well, if I have a deck of cards, right, and you know, let's see, I've got m choose 1. Well, if I have all of these a's, right, if I have n a's, why should it be n choose 1? Well, you know, I had n a's, and when I was multiplying together, I could pick this a, or this a, or this a, or this a. How many ways are there to choose 1a? Well, there are n choose 1 ways to do it. Okay? And that was kind of this proof that you had to sit there and think about for a while. It's a beautiful proof. I love that proof. This proof is horrible. But this proof, once you have it, is actually useful. Because let's say I wanted to write a program to do this. If I want a program to give me all of these binomial coefficients, right, what do? Well, I do it recursively, and then I have an addition step. Right? This tells me how to write a program for it. Okay? And it's not, the point is not for you to memorize and regurgitate this proof. Even if I could do that for this class, even if I could, right? If we were in an auditorium and I was giving you a test on paper and told you to regurgitate a proof, I would never ask for this one. Okay? It's too long and there are too many little details, and it depends on this little bit that I forget, right? It's not an easy proof, but it's mechanical. It's algorithmic, which is entirely different, right? This proof, unlike the other one, right? How are you going to teach a computer to do the card trick to figure out the binomial theorem? Okay? This one you actually could. All right, let's do another example. Okay, let's prove the freshman's dream prime version. No, it's not just to show induction. Okay? I mean, it is part of that, but it's also to show you that there's a way to make a computer do this. Right? The induction proof suggests a way to make the computer do it. How could I make a computer compute these binomial coefficients? Okay, if I wanted to create an algebra system to symbolically manipulate these things, how could I do it? Right? Well, there's a recursion right here. Okay. Let's look at freshman's dream. Let's revisit the freshman's dream. So this is the freshman's dream. There are a couple versions of it. And it goes like this. And there's even another one. Let's do a little lemma. Let me give you a little lemma first. Okay, this is just a little lemma. We'll use this later. If P is prime, then then in ZP, for all k not equal to 0, P choose k equals 0. Okay? So here's what I'm saying. If P is prime, then in ZP, for any k not equal to 0, P choose k equals 0. Okay? Here's a proof. So 1 to 5, how do we feel about that statement? Okay? Here's the proof. Okay? P choose k, you'll like this, equals P false k over k factorial, which equals P times P minus 1 times P minus 2 times ... times P minus k plus 1 all over k times k minus 1 times k minus 2 times ... all the way down to 1. Okay? Well, since P is prime, k minus 1, 2, do not divide into P. In other words, nothing on the bottom divides the first term on top. So P false k equals P times some integer. That's it. 1 to 5. How do we feel about that one? No induction, just straight numbers. Right? The fact is that nothing on the bottom here in k factorial can divide anything, can divide P. Why? Because P was prime. Definition of that. Nothing, no integers k minus 1, blah, 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 down to 2 will divide into P. That's all it says. All right. So, freshman's dream. Prime addition. If P is prime, then in ZP, for any posant in a plus b to the p equals a to the p times plus b to the p. Okay? It's just lemma. It's not, there's no name for this. This is just, I mean, if I gave it a name, it would be prime binomials, I guess. If p is prime, then in ZP for any posant and a plus b to the p equals a to the p, b to the p, plus b to the p. I'm going to leave that one for you. It's really, so just apply the binomial theorem and everything in the middle. I'll just do it, right? Proof. Apply binomial theorem. And from above, lemma, everything in the middle. Is 0. The only thing that's left are the two ends. All right. Do I have enough time? I'm actually out of time, aren't I? Great. I needed to get through, well, oh well. Okay, so what I wanted to do was I wanted to get through the proof for Fermat's little theorem. I didn't quite make it. I'll make it next time because the proof is very short. So next time we'll do that. There are actually a bunch of proofs for this. We'll do the induction one. And then after we're done with that, we'll start doing extended division algorithm. Which is interesting. But more importantly, we'll do extended Euclidean. I should say we'll do a division algorithm recursively. We're not going to do the extended version. So we're going to do division algorithm. Redux. And then we're going to do extended Euclidean algorithm. And our goal is to build an algorithm that can compute multiplicative inverses. All right, so that's our goal. So remember when we had that 1/2 bit? I wanted to get to division, but I wasn't able to. But remember when we had that 1/2 bit? What should I focus on? I mean, the point of this is to do another example of induction. At least this was. Okay? And then to be able to write a program from this. All right? So, I mean, what do you want to focus on? Well, focus on figuring out how induction works. These two things are a build-up to Fermat's little theorem. Okay? So this is why we did those two little things. So the little lemma, a freshman's dream, needed for this. Okay? And then we have we're going to revisit the division algorithm because what we're going to do with the division algorithm is we're going to look at it and we're going to start going, we're going to start looking at what happens when we do recursion on it. And then the extended Euclidean algorithm, the idea is to keep a hold of all the little things we do in between. Because what we're going to be able to do with those numbers is we'll be able to build an algorithm to compute multiplicative inverses. And this is something we actually need to do for RSA. We need to be able to see the computer do those computations. That's where we're going. Are there any other questions? Okay, so I didn't get it as far as I wanted to. We didn't make it to Fermat, but we did make it at least through the binomial theorem, which was like pulling teeth. I need to fix the other one. I got distracted by this thing, and I had it stated wrong, so this ate up all my time, which was annoying to me. So note to self, fix that for next time. That's it. Any other questions? Okay. Thank you.